Question number 26 says the rate law for the reaction represented by the equation above is rate equals K times NO2. See that you can see that it's first order. F2 is also first order. Which of the following could be the first elementary step if it's the slow step and the second step is fast? The fact that the second step is fast has nothing to do with it. If the slow step is the first step and that first step is the rate determining step, which it is, then we know that it has to be one NO2 and one F2 in the reactants. Because they're both first order, we know that we can use the stoichiometry of the slow step, the rate determining step, to determine the rate law. So therefore, A is not correct because it doesn't have NO in it at all. B looks like is the correct answer because it has NO2 and F2. C is incorrect because it only has F, not F2. And D is incorrect because it has that 2 in front of the NO2. So B is the correct response. Okay, number 27, the smallest bond angle. The smallest bond angle. These are both based on the tetrahedral shape. This has 4 bonds, no lone pairs. B has 3 bonds, 1 lone pair. So they're both around the 109.5 region. C has 3 bonds and no lone pairs, and D has 2 bonds and 1 lone pair. So those are both right around the 120 range of the trigonal planar. So which one's the smallest is definitely not C, definitely not D, because again, they're larger than 109.5. Okay, now between A and B, which of those two is going to be the smallest? Is this lone pair here, remember, increases the electron repulsion and pushes those bonds a little bit closer together. So on this one, you would say this one's slightly less than 109.5, where this one is a true 109.5. So B is the correct response there. Okay, question number 28 says a mixture containing equal numbers of moles of ethyl acetate and butyl acetate was separated using distillation. Based on diagrams above, which following identifies a substance that would be initially present in higher concentration in the distillate and correctly explains why. Okay, the distillate, remember, is based on distillation. Distillation is the gases that are formed when something is distilled. Okay, so which of those basically breaks apart easier is what the question is asking. So they're virtually the same molecule in that they've got this weird polar region kind of right here in the middle. This one does have a longer carbon chain there at the end. So we know that because that's going to have a larger electron cloud, this one is going to have stronger LDFs than the one on the left does. So the polarized, in terms of dipole-dipole, they're both very similar, but this one, it does have a larger carbon chain at the end, so therefore the larger electron cloud, it's more polarizable. So this one would have stronger overall intermolecular forces. Okay, and so therefore which one is going to be present in higher concentration, means which one's going to break apart easier, is ethyl acetate. So C and D are out. And remember, you don't break bonds when something goes from a liquid to a gas. So B is the correct response. So it's got a shorter carbon chain, has weaker London dispersion forces. Okay, questions number 29 through 31 deal with this information right here. Okay, let's see. We're starting with an absorbance of 0.62. It wants to know how long did it take for 75% of the initial amount of the C25H30N3 plus to react. So if the initial absorbance was 0.62, 25% of that would be, you'd be down to 0.45. If 50% of it had reacted, you'd be down to 0.31, so that would be right around here. And when 75% of it is gone, as reacted, you're down to, again, about 0.15, which is way down here. So the correct answer is 300 seconds, which is C. Number 30, what would be the effect on the reaction rate if the solution is diluted by a factor of 2? Well, if the concentration is diluted, we know that there's the particles that are in there. The spectrophotometer, the light travels through that cuvette, and as it travels through there, it hits the particles that are in there, and then changes directions. So it won't. So when you dilute that solution, dilute the solution, of course, more of the light is going to be able to pass through because the particles are more spread out. So what would happen to the reaction rate is, of course, it would be lower. Anytime you decrease the concentration, that's going to lower the rate of the reaction. Okay, and then question number 31. We can see that we have two different molecules. One molecule, this first one here, its maximum absorbance is way down at 200 nanometers, and then, no, that's incorrect. The dashed line, yes, is here. The solid line, this one here, its maximum absorbance occurs at a wavelength of right around 600 nanometers. Okay. So which of the following is the best wavelength? Is definitely not 205, because again, we're not talking about the dashed line, we're talking about the solid line. Okay, and why is that the correct form? Because remember, we're trying to absorb something, and in this case, we're talking about the color violet, and we know that the color violet gets absorbed significantly at, again, right around 600 nanometers. So the correct answer is C. Okay, question number 32, another equilibrium one. These are very common on the multiple choice. Okay, so on this one, you've got an equal number mole sample of CO and H2O. There is a 1-to-1 ratio, so we know, a 1-to-1 ratio. So we know that as the CO and the H2O react, that they're going to react they're going to disappear at the same rate. So we can say that we know that these two are going to be equal to each other. Okay, we also have a very, very large equilibrium constant, which means that as this reaction happens, you're going to end up having a lot more product than you are reactant. So let's go through our answers here. Is the concentration of H2O greater than the concentration of CO? No, we already said that since it's a 1-to-1 ratio and you're starting with the same amount, that those concentrations have to be equal throughout the process. So A is not true. B, H2O is greater than H2. We already said that with that large equilibrium constant, you have mostly product. So no, you're not going to have more H2O than you are H2. And again, like always, they always throw this answer in here as well. No, equilibrium does not mean all of them are equal to each other. Again, we have way more product than we do reactant. The concentration of CO2 is greater than CO. We know that's true because of the large equilibrium constant. The correct answer is C. Question number 33. If I remember correctly, yeah, this is a tough question here on 33. Okay, so on 33, you've got a silver concentration of 0.02, and you've got a lead concentration of 0.001. Okay, and it says a 0.010 mole sample of K2SO4 is added to the solution. Based on the information table above, which of the following will occur? So will it precipitate form? If it does, or will both of them precipitate? Or will only Ag2SO4 or PbSO4 precipitate? So in this case, they're giving us a concentration of Ag+, which is this, and then the concentration of SO4, which is this. So what we've got to do is this is a Q situation where we have to figure out the Q for both of these, which is, again, this is definitely a more than 90-second question. So for silver, it's Ag2SO4. So when we split that apart at equilibrium, we get 2 Ag pluses plus SO4 2 minus. So for Ag, we've got 0.02, and I'm going to leave that last zero off just to save some space, and that has to be squared, because there's two of them, times 0.001. Okay, so 0.02 squared is the same, that's 2 times 10 to the minus second, so that's squared, so that becomes 4 times 10 to the minus fourth. And then we're basically going to move this 3 more spaces to the left. So the Q value for Ag2SO4 would be 4 times 10 to the minus seventh. Okay, now in this case, Q is 4 times 10 to the minus seventh. KSP is only to the minus fifth. So therefore, we know that Q is less than K. And when Q is less than K, we know the reaction is going to proceed to the right. And if it proceeds to the right, that means it is not going to form a precipitate. If it proceeds to the left, remember, here's our equation right here. If it proceeds this way, you're going to form a precipitate. If it goes this way, it doesn't. Okay, so Ag2SO4 will not precipitate. Okay, so we know that B is out and D is out. So now it's just a matter of will the lead sulfate precipitate or not. So with lead, we've got, again, PbSO4 in equilibrium with Pb2 plus SO4 2 minus. And so it's a 1-to-1 ratio, so Q in that case is going to equal 0.001 times 0.001, which is 1 times 10 to the minus third, which becomes 1 times 10 to the minus sixth. And here the KSP value is 1 times 10 to the minus eighth, so Q is greater than K. So that means only PbSO4 will precipitate, which is C. Okay, number 34, the pH of a 0.01 molar HNO2 solution is in which of the following ranges? So they give us the Ka value, so we've got HNO2 in equilibrium with H plus and NO2 minus. So this is where we could do an ice table here. This is 0.0100 minus X plus X plus X. X, and 0.01 minus X. Okay, so then for our K value, we'd go 4.0 times 10 to the minus fourth equals X squared over 0.01 minus X. Take the minus X out. So X squared would equal 4.0 times 10 to the minus sixth. So we have to take the square root of that, and X would equal, the square root of 4 is 2. The square root of something to the minus 6 is take half of it to the minus 3. So that means that X, which is equal to the hydrogen ion concentration, is 2 times 10 to the minus third. And then again, to estimate the pH, we use that number up in the corner. We know the pH is somewhere between 2 and 3. So it's that number and then one number less. So the correct answer is certainly B. Okay, question number 35. The 1s electrons of calcium 2 plus and argon are shown above. So calcium, remember, look at the periodic table, has 20 protons. Argon only has 18 protons. But calcium with that plus 2 charge does have 18 electrons and 18 electrons. So clearly the attraction in calcium 2 plus is going to be greater because it's got more protons than argon does. So which of the following correctly identifies the species associated with peak X and provides a valid justification? So peak X is farther to the left. It has a greater binding energy than the one on the right. And therefore that would be calcium because, again, it has more protons than argon does. So the correct answer there is D. Okay, number 36. A vessel contains argon at high pressure. Which of the following statements best helps to explain why the measured pressure is significantly greater than the pressure calculated by the ideal gas law? So again, when do gases behave like an ideal gas is when remember there's two things that we assume with a kinetic molecular theory, that molecules aren't attracted to each other and they don't take up any space. So when argon is at a high pressure, it does take up more space than we would actually presume it to with the ideal gas equation. Okay, So when it takes up too much space, then that volume that it does take up, that we presume it doesn't take, it does take some of it up. So the correct answer is D. The combined volume of argon is too large to be considered negligible. Okay, numbers 37 through 39 deal with the following information here. So you've got some big nasty equation. You've got an exothermic reaction. You've got a negative delta S. Okay, and 37 says 2 trials are run using excess water. In the first trial, you got 7.8 grams of the sodium peroxide, and you got 3.2 grams of sulfur. In the second trial, you get 7.8 grams of sodium peroxide and then 6.4 grams of sulfur. So you're doubling the amount of sulfur that you used in the first trial. Both of them react as quickly as possible. Both trials yield the same amount. Both trials yield the same amount of SO2. So what does that tell you about the sulfur? Okay, why did this reaction stop? Because you ran out of sulfur in both cases. Okay, if you had run out of the Na2O2, well, then you would know that the sulfur was not the limiting reactant. Okay, but in this case, you know that the sulfur it didn't matter the amount of sulfur that you had. So I think I said that backwards. Sorry. Let me back up here. Because the amount of sulfur was different and you still ended up with the same amount of product, that means that what did you run out of first is you ran out of the Na2O2. Sorry, I think I said that backwards. Okay, because the amount of sulfur changed, yet the experiment still ended with the same amount of SO2 produced, that means that the Na2O2 has to be the limiting reactant. So A is out and B is out. Okay, so now if that's the limiting reactant, then we know that that's the one that we use to figure out how much heat is produced or released from this reaction. So they give us an enthalpy change of negative 610. Okay, and now we have to use that to figure out the Q value. So we know that we have 7.8 grams of the Na2O2. So 7.8 grams, and then there are 78 grams in 1 mole of Na2O2. Again, convenient how it's 1/10 of that amount. Okay, and then we can say, now here's where you got to be careful. 1 mole of Na2O2, I should say there's 2 moles of Na2O2 in 1 mole of the reaction, and then in 1 mole of the reaction you've got 610 kilojoules. Okay, and again, you're not going to be perfectly right, but that's 1/10. So 1/10 of, so take those, that's 0.1. So 0.1 times 610 is 61. 61 divided by 2 is roughly 30. So the correct answer is C. Okay, number 38, atoms of which element are reduced in the reaction? So reduction means, remember that the oxidation number is reducing. It means you are gaining electrons. So in which case are electrons being gained? In this case is you've got the Na2O2, so sodium's +1 and oxygen is -1. And then over here on the product side, you've got sodium hydroxide, where the oxygen's -2, and then sulfur dioxide, where the sulfur is going to be +4 and the oxygen is -2. So in both cases, oxygen is -2 on the product side, but over here it's -1. So its charge is being reduced, and by reducing that charge, that is the reduction process. So the correct answer is C. Okay, number 39, which is the following statements about the thermodynamic favorability, remember that is delta G, is correct at 298. So we can see that delta H is negative and that delta S is also negative. So we know that when the temperature is low, that is the bigger factor. That is the driving force behind the reaction. But as the temperature increases, that starts to play more of a factor. Okay, so at 298. So which of the following is correct? It does say a redox reaction occurs. So we do know that it is thermodynamically favorable because the reaction happens. So it is not thermodynamically unfavorable. Okay, and now it's just what's driving this reaction forward. Remember that with that equation, delta G equals delta H minus T delta S, that in this case, you've got this component and this component. When delta S is negative, this whole thing here becomes positive. So it is not driven. When delta S is a negative value that we have up here, that does not help it become more thermodynamically favorable. So it's not driven by that at all. So in this case, it is driven by the enthalpy change, which is C. Okay, question number 40 says, based on the bond energy shown in the table above, which of the following diagrams best represents the change in energy as the reaction represented below proceeds? Okay, so in this case, you've got an HH bond, which has to break, so that's 430. You've got a Cl2 bond that has to break, so that's 240. So the bonds that are breaking are 670. And then you've got HCl, and don't forget, you've got two of them. So you've got 430 times 2, which is 860. So the amount of energy it takes to break the bonds is 670. The amount of energy that gets released when the new bonds are formed is 860. So it takes some energy to get up, and then it releases more as it comes back down. The difference between those numbers is 190. So A is the correct response. It absolutely is an exothermic process. Obviously on B, that number is incorrect. C has it being endothermic, which it's not. And D also has it being endothermic. Okay, question number 41. Based on the ionization energies of element X, given the table above, which of the following is most likely the empirical formula of an oxide of element X? So really what we're trying to figure out here is where's the big jump. Clearly it happens between the third and the fourth ionization. So that means this element does have 3 valence electrons, which it's going to lose. So that's going to be X 3 plus and O 2 minus. So when you form a compound with that, you're going to switch those, which becomes X2O3, which means the correct answer is C. Okay, question number 42 says a 0.10 mole sample of each of the 4 species in the reaction represented above is injected into it. So you're starting with 0.10 moles of all of this. Which of the following species will have the highest concentration when the system reaches equilibrium? So you're starting with 0.10 moles. So you've got an initial value for all of these. You have an equilibrium system. So you do have to calculate Q. So it's products 0.10, and that's going to be to the 4th power over, and then we've got H2S, which is 0.10, and that's going to be squared times CH4. So that one cancels, that one cancels. Those 2 are going to cancel, and we're going to be left with 2 up here. So Q is going to equal 0.01. Okay, which is 1 times 10 to the minus second to the minus second. Either way, it doesn't matter. It's either way, because K is to the minus 4, so therefore Q is greater than K to start, which means we know the reaction is going to proceed to the left. If it proceeds to the left, it means you're going to make more reactant rather than product. And since for every 1 CH4 that gets made, you're going to make 2 HS's, the correct answer is A. H2S will have the highest concentration at equilibrium. Okay, number 43. A sample of ice is heated to liquid water and then to water vapor. The heating curve is shown above. Which of the following lists the signs for the changes in enthalpy and entropy for the process for segment X going from left to right? So starting here and going to here. So remember, here you have a solid, here you have solid to liquid, here you have liquid that you're warming up, Here you're going liquid to gas, and here you're just warming up the liquid or the gas even more. So this is the process by which the liquid is turning into a gas. So the liquid particles are breaking apart, turning into a gas. So to me, the easy part there is the entropy. Okay, the entropy, you're going from molecules that are stuck together into a gas that's very much more disordered. So that is a positive delta S. So that means that A is out and C is out. Now, in order to break those attractions between the water molecules, it requires energy to do that. And remember, anytime you go solid to liquid, liquid to gas, that's always a positive delta H. That's an endothermic process. Anytime you go in the opposite direction, gas to liquid or liquid to solid, that's a negative delta H. That's an exothermic process. So in this case, you're going from a liquid to a gas. That's a positive delta H. The correct answer is B. Okay, 44 to 47 deal with this information. The reaction does go essentially to completion. It does take place in a rigid insulated vessel that's at 600. Okay, number 44. What happens to the temperature of the contents of the vessel as the reaction occurs? Well, as the reaction occurs, we can see that delta H is a positive value. That means it's absorbing heat from the surroundings. So remember, the system is the reaction itself. The surroundings is the vessel, whatever else is in there as well. So what happens to the contents of the vessel means the surroundings. So anytime you have an endothermic process, it has to take heat or energy from those surroundings to make the reaction happen. Okay, and so the correct answer is C. You're taking heat from the surroundings, so the temperature must decrease because that reaction is endothermic. Okay, on 45, a sample of CH3OH, so that's our reactant here, is placed in the previously evacuated vessel with a pressure of 600 Kelvin. What is the final pressure in the vessel after the reaction is complete and the contents of the vessel are returned to 600 Kelvin? Well, initially there was one particle of gas, and that one particle of gas has now turned into 3 particles of gas. And remember, it goes essentially to completion. So all of that CH3OH is now gone, and now you simply have 1 carbon monoxide and 2 hydrogens. And again, since pressure is equal to nRT over V, and N is the number of particles, if we had 1 mole of CH3OH, well, now we have 3 moles of product. And whatever the amount of CH3OH you had, that amount has now tripled, which means the N value has tripled, which means your pressure must also triple. So the correct answer is D on 45. Question number 46, what can be inferred about delta S for the reaction at 600 Kelvin? Again, you're starting with 1 gas, you're going to 3 gases. 3 gases is much more disordered than 1 gas. So we know that delta S must be a positive value. So B is out, D is out. Okay, and it must be positive since the reaction is thermodynamically unfavorable at 600 Kelvin. Well, it goes essentially to completion, so I don't think that it's thermodynamically unfavorable. Okay, C, it must be positive. Why must it be positive? There's lots of reasons why. Because you're going from 1 gas to 3. Because the reaction goes essentially to completion, which means the reaction's happening. And if the reaction's happening, delta G must be a negative value. So C is correct. The only way for delta G to be negative, if delta H is positive, is if the delta S value is also a positive value. Okay, 47. Which of the following statements about the bonds in the reactants products is most accurate? Again, it's an endothermic process. If it's endothermic, that means it took more energy to break the bonds than the amount of energy that gets released when the new bonds are formed. Okay, so it says on A, it says the sum of the bond enthalpies of the bonds in the reactant is greater than the sum of the bond enthalpies in the products. That is the correct answer. Okay, the sum, all of those bond energies in the reactants has to be greater than the ones in the products. Here it says less than the length of the bonds. I don't even know what they're talking about there, and whether they're polar or non-polar doesn't matter. Clearly they had a hard time coming up with some wrong answers here. Okay, because anytime they talk about enthalpy and bond energies, it's about comparing the reactants to the products and which one has the greater bond energies. Okay, number 48. Which of the following correctly ranks the three monoprotic acids listed in the table above from weakest to strongest? Okay, so first of all, this one has the weakest or the lowest concentration, but still has the lowest pH. So remember that acid strength is how much of that acid dissociates and breaks into hydrogen ions. Okay, and so the lower the pH, the more hydrogen ions there are. So when one acid is at a lower concentration but still has the lower pH, that means it has more hydrogen ions than the other two do. So therefore, absolutely, acid X is the strongest acid. Okay, and so that is right here, which means A and B are out. Okay, now between Y and Z, again, use that same logic, that Y has a lower concentration, yet they both have the same amount of hydrogen ions. So whichever one has the lower concentration but produces the same amount of hydrogen ions, so this one has more acid particles in it, but doesn't produce as many hydrogen ions as, it produces the same amount of hydrogen ions as the 2 molar one does. That means that acid Y is a stronger acid than acid Z is. Because again, at a lower concentration, if it produces the same amount of hydrogen ions, that means it's a stronger acid. That means more of that acid is breaking apart than the 3 molar one is. So Y is a stronger acid than Z is, which means the correct answer is D. Okay, number 49. Based on the information above and the periodic trends, which of the following is the best hypothesis regarding the oxide formed by rubidium? So rubidium is also in that same column. Notice that as you go down, you start to, there's more compounds that are formed. So rubidium is right below potassium. And so, again, you would presume it would form at least that, maybe even more, because as you go down, you can see you're making more and more oxides of it. Okay? So if sodium does it, potassium does it, and as you go down, again, the higher ones don't do it, you can presume that rubidium would also do the same thing as sodium and potassium, which means it is D. And then number 50, when a student adds 30 milliliters of 1 molar HCl to a 0.56 grams of powdered Fe, a reaction occurs according to the equation above. When the reaction is complete at 273 in 1 atmosphere, so remember that is STP, and at STP, remember that 1 mole of any gas has a volume of 22.4 liters. Which of the following is true? So they're talking about excess reactants. So that's probably one of the things we need to figure out first is what's the limiting reactant here? Because they give us an amount of HCl, they give us an amount of iron. Okay, so let's go ahead and I think the way that I did is I took the 0.56 grams of Fe, and then the molar mass of iron, again, it's 55.8, but on a free response or a multiple choice question, 56 grams in 1 mole of Fe. And then we can say that according to the balanced equation up here, 1 mole of Fe is going to react with 2 moles of HCl. So 0.56 over 56, so 5.6 over 56 would be 0.1. So 0.56 would be 0.01. So 0.01 times 2 would be 0.02 moles of HCl. And remember, that's how much HCl we need. Now, how much HCl do we actually have? Well, we have 30 milliliters, which is 0.03 liters times 1 molar equals 0.03 moles of HCl is how much I actually have. Okay, so if I only need 0.02 moles of HCl, but I have 0.03 moles of HCl, that does mean that I have more HCl than what I need. Okay, which means that iron is the limiting reactant, and therefore HCl is the excess reactant. Okay, now, just because that's true doesn't mean that A and B have to be right. So A and B are correct. HCl is in excess. Now, how much is going to be left over? Well, you need 0.02, but you have 0.03. So how much HCl is left over would be 0.01 moles left over. So notice in A it says 0.1 moles, not 0.01 moles. This is a tricky question. Okay, so A is not correct. Okay, 0.02 moles of HCl remain unreacted. Nope, still 0.01. So B is not correct. Okay, and so now the excess reactant ones, those are out. And usually that's, normally when you have two answers that are pretty similar, usually one of those is the right answer. But in this case, that's not. That's another reason this question is a tricky question. Okay, so now let's look at how much product will be produced. So we know that the iron is the limiting reactant. So if we take again our 0.56 divided by 0.06, we already said is 0.01 moles. So we know we have 0.01 moles of Fe. And now we can look at C and D. So they're asking about, or they're saying that 0.015 moles of FeCl2 is produced. So let's go to our balanced equation here. 1 mole of Fe is going to make 1 mole of FeCl2. And hopefully at this point, this is the last question. Hopefully you've got some extra time here because clearly this is taking more than 90 seconds. And then 1 mole of FeCl2. Now I have to figure out the molar mass. So 71 for chlorine plus 56 is 127. 127 times 0.01. Oh no, I'm sorry. They're only asking about moles. I went farther than I needed to. So no, you don't have to get grams of FeCl2. Sorry about that. Just moles. Well, 0.01, and then it's a 1-to-1 ratio. It's 0.01 moles of FeCl2. Okay, so that says 0.015, so C is a no. So at this point, you can stop and say, well, D has to be the right answer then. Or you remember that, again, at STP, 1 mole of any gas has a volume of 22.4 liters. So remember, we did produce 0.01 moles of FeCl2. Okay, and we also know that 1 mole of hydrogen gets produced as well. So here, same thing. Instead of 1 mole of FeCl2, we could just change that to hydrogen. And so 0.01 moles of hydrogen are produced. And 0.01 moles times 22.4 is 0.224 liters of hydrogen is the correct response. Okay, so D is the correct response there. So there were a couple of questions definitely in this last section of 26 through 50. There was the KSP one that's definitely a more than 90 seconds. This one is definitely more than 90 seconds, and that's okay. So give yourself a score, add them all up, get your score out of 50, please. I got a 49.5, which isn't possible. You got to get a whole number. So just kidding, I didn't get a 49.5. Okay, so add those up, and then we'll start the free response tomorrow.